Welcome to Earth Science Lecture. This is Professor Diana L. Pomeroy. This week, we're going to begin an overview of oceanography. Oceanography is a survey of the properties of the world's oceans. In this part of the overview, we're going to learn about the distribution of the world's oceans, the chemistry of the ocean, and how waves are formed on the ocean surface. About 71% of the Earth's surface is covered in water, and 97% of that water is part of the global ocean. Recall that the oceans first formed on Earth's surface over 4 billion years ago, likely due to plate tectonic activity and impact from comets and asteroids. The global ocean is divided into 5 major oceans. These are as follows. We have the Pacific Ocean, the Atlantic Ocean, the Arctic Ocean, Southern Ocean, and Indian Ocean. The oceans are further divided into seas. This map shows most of the major seas of the world. Seas are larger inlets than bays, with a direct and open connection to an ocean, and have greater variability in their salinity than the oceans have. In Southern California, we have the Pacific Ocean and the Gulf of California as our ocean and our sea. Here is a map of both the California coast and the Baja Peninsula, with the Pacific Ocean and Gulf of California labeled on each. The oceans and seas of Earth have one thing in common. They're primarily made of 2 chemical compounds, which are water and salt. Water is a polar covalent molecule with a bent structure. Water's unique shape allows it to behave differently from other molecules as a solid, liquid, and gas. Recall that a covalent bond is formed when the outermost, or valence, electrons between atoms in a molecule are shared. In water, the structure is polar because the oxygen atom has a slightly negative charge, while the hydrogen atoms have a slightly positive charge. This difference in electronegativity is called polarity. The way that the molecule is structured overall, where the hydrogen atoms bond at a 104-degree angle to the oxygen atom, is called a bent geometry. This structure is very difficult to break. Covalent bonds within and hydrogen bonds that develop between other neighboring water molecules make water remain in a particular phase, either as a solid, liquid, or gas, for longer than other substances. Water structure also causes it to have other distinctive properties that set it apart from other molecules. Liquid water is known as the universal solvent. A solvent is a substance that can dissolve other substances, and water can dissolve practically any other substance that it comes into contact with due to its polarity. As a solvent, one rule tends to be especially true for water. Like dissolves like. Substances that are hydrophilic, that prefer to bond to the water molecule, are typically polar and will be dissolved in water. Salt and sugar are examples of this scenario. Substances that are hydrophobic, that do not bond to the water molecule, are nonpolar. Water and oil, as pictured in the glass, do not mix because water is polar and oil is nonpolar in its structure. The hydrogen bonds between different water molecules allow for 2 unique properties of liquid water. These are cohesion and adhesion. Cohesion is when water molecules bond to themselves, such as in this water droplet. Adhesion is when water molecules adhere or bond to other surfaces, usually from a combination of hydrophilic and hydrophobic interaction. The best example of adhesion is when you drink water through a straw. As you drink, the water sticks to the sides of the straw, allowing it to move up. The same phenomenon happens with any form of liquid water. Recall that in rivers, as water moves through a channel, it adheres to the river banks and river bottom, and through cohesion it will flow as one body across the Earth's surface. Water will replace itself as sections of the river bank erode, causing the channel to curve over time. The same thing happens in the ocean with wave action. As waves are displaced during the process of breaking as they hit shore, water rushes to replace the molecules in a back and forth motion. This is again a demonstration of both cohesion and adhesion. Liquid water has a high surface tension, meaning that the hydrogen bonds are especially strong at the uppermost section of any water body. Think about overfilling glass. If you do, you'll notice that the water won't spill over right away, because the energy required to break those bonds at the surface is far more than at depth. And so in this diagram, we've got a photograph of a beaker that's pretty much overfilled, and you'll notice the paperclip is floating on top of the beaker, and it's able to do this because it has a high surface tension. So water's high surface tension allows for objects that have a lesser density to float on top. So paper clips, on the ocean we have various creatures that can float on the surface of the ocean. You can have boats and things also. Again, this is all due to water's high surface tension, those strong hydrogen bonds at the surface. All the properties of water I've discussed so far can be applied to any moving body of fresh water, but the ocean differs from the rest of water under the surface because it's saline. It has salt in it. Now, in addition to salt, there's other dissolved compounds and components that we find in seawater. So those are actually covered in another lecture that I have posted on YouTube. Those are covered under the Oceanography marine sediments lecture. So if you want to find out more about those types of sediments, go ahead and watch that. So for this class, let's focus on salt as our main component that's dissolved in seawater. So salt originates from the land. As rainfall moves through the landscape and erodes it, minerals collect and become deposited in the ocean. So those minerals that get deposited, most of them that slough off will, remain as solid rocks, but some of it will actually further break down into chemical components. Most of those are sodium and chloride, those ions that we find in that solution. So this pie chart shows the proportion of salt in the ocean. On average, for every 1,000 grams of salt, or every 1,000 grams of water in the ocean, there's 35 grams of salt. So the ocean has a salinity of 35 parts per 1,000 on average. So again, for every 1,000 grams of water, approximately, there's 35 grams of salt in the ocean. And so that makes it 35 parts per 1,000 saline. So most of that salt, again, is a combination of sodium and chloride, as you can see in the pie chart. However, there are other elements that are present from those other sediments. A lot of sulfates and magnesium, calcium, and things. Those elements are present, again, from other rocks and minerals that break down in the seawater itself. This slide has a diagram of a water bottle that has been divided into 4 categories of salinity. Note that fresh water, including groundwater, has a very low salinity, which is less than 1 part per 1,000. Some places on Earth, like the Red Sea, have a higher salinity than the ocean, and that's due to excess evaporation and limited mixing of those waters with the open ocean. Salinity of a coastal environment changes in different places, depending on what parts of the water cycle are affected. This is connected to climate belts, which correspond to different latitudes, as well as changes to seasonality. Salinity of the ocean decreases, so it goes down, with increases of the following. Increased precipitation will decrease the salinity of the ocean. Increased runoff from snowmelt. Increased runoff of rivers and streams, so from excess rainfall. And also increased groundwater discharge. So with groundwater, as it seeps to the surface, sometimes it will discharge and meet the surface again. And so all that runoff collectively, as it hits the surface of the ocean, will decrease the salinity in that particular area. Salinity of the ocean will increase with the following phenomena as part of the water cycle. It will increase with increasing rates of evapotranspiration, a process that tends to occur in various species of plants. Evaporation of the surface waters of the ocean will increase salinity in some places, as well as the increase of an expansion of glaciers or the presence of snowfall in different places. All of this will increase the salinity of the ocean in that particular location. Solutions in nature, that includes water as one of them. They're acidic, basic, and neutral. Water is a chemical that's considered neutral because it has an equal amount of two materials in it. Hydrogen as an ion and hydroxide as an ion. The hydroxide ion is oxygen bonded to one hydrogen atom. So it has the structure of OH with a negative charge. Hydrogen as an ion has a positive charge. So you combine both of these together to make water, H2O. So pure water is considered neutral because it has equal amounts of hydrogen and hydroxide in its solution. So when we have an acid, there's more hydrogen ions present in a solution. When we have a base, there's more hydroxide ions in solution. So on this diagram, we have the pH scale. We have acidic on the left from 7 down to 0, and we have alkaline or basic on the right from 7 to 14. Note also there's color variation here, and this is due to what we call the litmus test. So if you're testing the pH of a substance, whether it's your backyard pool or whether it's your water supply from your tap or any kind of solution, if you want to test the acidity, you get a strip of paper called a litmus paper test, and you place it in that solution. The litmus paper will turn a color based on whether you have an acid or a base. So if you've got an acid, the litmus paper will turn pink. If you have a base, it will turn blue. And again, this is due to the chemical reaction in the litmus paper itself, but essentially it's based on the number of ions in solution. So the more hydrogen ions that you have, the lower the pH. The more hydroxide ions that you have, okay, the greater the pH. So pH is an inverse proportion based on the concentration of ions, of hydrogen ions in solution in particular. So acids again have a range of pH from 1 to 6, and bases have a pH of a range from about 8 to 14. Neutral solutions like pure water has a pH of 7, so it's perfectly balanced in between that scale from 0 to 14. So some everyday substances on Earth that have different acidic and alkaline values, some examples would be like semic acid, which is essentially hydrochloric acid that has a very low pH. It's very acidic. It has a pH of approximately 2. In terms of alkaline, think of maybe lye or soap. Most cleaning solutions that we have, like lye or soap or bleach, they're fairly high on the alkaline scale. So they tend to have maybe 11 or so of a pH in that way. So what about seawater? Well, seawater has dissolved components in it, right? So it's got a lot of salts and other dissolved components like we saw on the previous slide with the pie chart. So its concentration of hydroxide is going to be a little bit greater than that of pure water. So its pH is slightly basic. It's got a pH of about 8. So again, that's not something for the ocean to take offense over. It's just a natural phenomenon where the pH is going to be about 8.1 on average for our oceans. So that means that our pH is slightly basic. And if we add excess carbon dioxide into the atmosphere, it's going to cause the reaction that's shown here, which is the carbonic acid buffering system, to move in one direction or another. So if you add excess carbon dioxide to an atmosphere on Earth, to the atmospheric concentration on Earth, that's going to throw off this equation. It's going to make it run in the forward direction. So according to Le Chatelier's principle, right, we have an equation at equilibrium. That's why there's two arrows in this chemical equation. So the equation can either go in the forward direction, be read from left to right, or it can go in the reverse direction, be read from right to left. So if we move in the forward direction, we're adding carbon dioxide to this equation. So we're pushing the reaction in the forward direction. And as we do that, you'll see that the very end product of this is excess hydrogen ion in solution. As we increase the concentration of hydrogen ion in solution, the pH is going to drop. And that is what we're expecting to see in the future with our ocean pH. Our oceanic pH is going to go down in value from 8.1 to about 7.5 or so. Now that's projected. If we continue to increase carbon emissions the way that we have been, if we're as dependent on that as we have been in the past couple hundred years, and our emissions do not change, then that is what we're going to be seeing. And we're already seeing this situation with the bleaching of coral reefs globally, where this bleaching process happens due to excess hydrogen ions in that water solution. The corals themselves, the organisms will begin to die, and as this happens, their external skeletons will start to turn white and collapse. And that's what we've been seeing globally, with the exception of places called hope spots, which were put together by a team of oceanographers, including Sylvia Earle, around the world, to essentially preserve a lot of our reef systems and our oceanic ecosystems to the best of our ability. So that's what we're going to be looking at in the future, is a lower pH and more acidic ocean, in addition to sea level rise, which I've covered previously with air-sea interactions and changes to our climate over time. So the acidity, or the pH of seawater itself, is maintained through that phenomenon, that equation that I showed you in the previous slide. This is known as the carbonate buffering system. So carbonates themselves are connected to a type of mineral. So carbonates are, through data classification, they're a type of mineral, specifically calcite in this instance. And this carbonate molecule, as it bonds to calcite, can build up the shells and structures that are necessary for different marine organisms to survive in the ocean. And the buildup and breakdown of those shells and structures is essential for maintaining the pH. And so both of these illustrations from the National Oceanographic and Atmospheric Administration show this phenomenon of the breakdown of those structures based on the amount of carbon dioxide in our atmosphere. And so even throwing off the proportion of carbon dioxide just by a couple of, hundreds or thousands of a percent is enough to cause this chain reaction to take place. So carbonic acid itself, which is H2CO3 in this, carbonic acid is a buffer. So in other words, this is like the midpoint. It can cause the reaction to either go forward or reverse. And again, that's dependent on the starting point. It's dependent on how much carbon dioxide that we have in the beginning. And so subtle changes are all it takes for this process to happen. Variability in sea surface temperature, pH, and the salinity of the oceans will lead to changes in atmospheric chemistry, temperature, and pressure. And this in turn will cause changes in climate over, again, spans of thousands to millions of years of time. So as the surface of the oceans continues to warm, the atmosphere will as well. This will lead to more extreme changes in weather, and we've been observing this, right? Just, I think, last week, there's a snowstorm that's headed back east that's of historic proportions. So what's happening is that polar front is being diverted. It's being pushed further down. Our subtropical jet stream as well is being moved as well. And so all of these movements of air masses are dependent on the surface of the ocean, because remember, it's rates of evaporation it's evaporation that actually starts the water cycle. And so if we have a warmer ocean overall, we're going to get much more storm activity and much more extreme weather, not only in the summer with extreme heat, but also in the winter, and summer and winter storms are going to be much more severe in future if we don't start curbing emissions now. So moving on from weather and climate, and with moving on from ocean chemistry, let's get into waves, because really wave action and circulation of the ocean are a big part of atmospheric change and a big part of climate as well. So there's two major types of waves that I'm going to discuss with you in our overview of oceanography, and these are atmospheric waves and ocean waves. Atmospheric waves include gravity waves and planetary waves. Gravity waves are compressional waves that generate turbulence in the upper atmosphere, especially over mountain passes. Planetary waves are developed as the Earth rotates on its axis, and these move along each major latitude, in turn generating weather patterns in the atmosphere. Rossby waves are a type of planetary wave that moves the polar jet stream south. And again, that's what I was describing to you on the previous slide. It can generate hurricanes and or cyclones, depending on where you are, at lower latitudes due to that disturbance as well. So this is why we get hurricane season in different parts of the world, is from these Rossby waves, these planetary waves that are just due to the fact that the Earth's rotating on its axis. So if the Earth didn't rotate on its axis, we wouldn't have our storm systems moving anywhere at all. In addition to that, the gravity waves that are felt in the upper atmosphere would not exist either. And so think of gravity waves as if you're in an airplane, for example, right? You fly above the weather, you're in the tropopause, so you're not in the troposphere, which again is the atmosphere in general that I've been describing and discussing with you so far. So the tropopause is above the atmosphere, about 12 kilometers up, and it's here that a lot of airplanes will fly. And whenever there's turbulence, if you're in an airplane during turbulence, that's because of those gravity waves. So as those waves pass through the atmosphere, it actually creates a set of wave motion due to passing over, like, let's say, an obstacle like a mountain on the land surface. And that in turn is going to cause turbulence. And so that's all that is. So again, gravity waves, planetary waves. There's a definite waveform motion, and it's like an S shape, right? There's a distinctive shape to that wave motion. So it's not only in atmospheric waves, but it's also in our ocean waves. So changes to pressure and temperature in Earth's atmosphere from planetary waves can form weather fronts and storm systems, and these will move over the oceans and onto land. So this slide has changes to the polar jet stream once again from that Rossby wave, that planetary wave, which can push strong and severe snowstorms much farther south during different seasons and during different years. So again, note that it's got that distinctive like curvature, right? It's got the distinctive curvature to that motion. And that's what happens with our ocean waves. So ocean waves are formed due to a disturbance in the surface of the ocean. When still water is disturbed, such as when a rock is dropped into a still pond, oh, I don't mean something like this. I mean something like this image here, right? So if you take a rock and you drop it into a still pond, tiny waves or concentric rings will form, and they'll move outward from that source of disturbance. So there's many different ways that ocean waves can develop. They can form in this way, which are known as tsunami, and I'll cover those at the very end of the lecture for today. But there's also wave action that occurs due to the wind, and that's the more common form of disturbance that makes our ocean waves. So this image shows some waves on the open ocean, and these are the waves we tend to think of. Again, these are caused from the wind. The speed, direction, and duration of the wind over the open ocean can cause changes to wave shape. All waves, whether they're waves in the open ocean, from the wind, sound waves, or atmospheric waves, have several terms that are in common with each other, and they have similarities in their shape. The terms that they have in common are as follows: the crest, the trough, wavelength, wave height, period, and frequency. The crest is the highest point of the wave, and the trough is the lowest point of the wave. Wave height is the difference in distance between the wave base, which is shown here as a dashed line in the first diagram from Khan Academy, and the crest, or the uppermost point of that wave. Wave period is the time that's required for a wave to finish a cycle of movement, or to move from point A to point B, as shown on this diagram. Wave frequency is the number of times a wave crest will move past a given point. In this example, the number of times a crest hits point A would be the frequency of the wave. So in this instance, just pretend that this wave is moving, right, on this image. And if the wave is moving on this image, let's say 2 cycles, you would have 2 crests that are passing by point A per, let's say, second, right? So those times, those frequencies are variable based on differences in wind strength, speed, and then wave shape. So again, wave period is variable as well, and waves that tend to have longer periods include the tides and tsunami. Okay, so those are special types of waves that are not generated by the wind. So wind action generates a much shorter wave period on average. And again, frequency is really variable depending on the obstacles, the currents. All of this has an effect on how many times a wave will move past a certain point. Ocean waves have both transverse and orbital motion combined together, and they move continuously until their energy dissipates at the coast. Once waves feel bottom, so in other words, the wave base meets the shoreline, meets the coast, they break into distinct forms. Transverse motion is a single point of disturbance that generates a continuous large wave series with a distinct S-curve to that wave motion. The slinky illustrated in these diagrams demonstrates transverse wave motion. Orbital waves are generated within ocean waves in addition to that transverse wave motion that I discussed with you previously. Orbital waves move in a circular pattern. They have a wave base or a limit to the orbital motion path, and they flatten out as the ocean approaches land. This GIF of a gull sitting on top of a wave shows the orbital motion beneath it, causing it to move, yet not change its initial position. So in other words, the gull itself is just moving in a circle. It's not moving really technically anywhere, just moving in a circle. So that type of motion is the type of motion that often gets us seasick. The strength of orbital wave motion diminishes in deeper water, and it compresses as waves break onto a land surface. Once waves reach land, they slow down and then they break, and this is due to that frictional force of the land surface and the slope of the continental shelf as well. So waves that wash ashore are called breakers. There are 3 categories of breakers, which are illustrated and photographed on this slide. These are plunging breakers, spilling breakers, and surging breakers. The difference between each of these, as you'll notice, is the land slope. With a plunging wave, the land slope has a greater angle than with the spilling wave. So notice that the slope is much greater here with a plunging wave. Surging waves can't break over the land surface, and they just slosh around rather than crest over and flood the landscape. So actually, surging breakers have the greatest land slope out of all 3. Plunging breakers are a good midway point. The land slope is just enough to create this wedge, and in turn that creates that curl of that wave motion that surfers and bodyboarders and those individuals that like to parasail as well, you'll take advantage of that, right, of that wave, the plunging breaker shape. Spilling breakers are more common in parts of Seal Beach. That's what we tend to have here. And then we have surging breakers. These tend to happen in storms or in areas where we have a really steep continental shelf and slope. When waves meet a land surface, they not only break, but this land surface itself, the shape of it, can influence the pattern of wave flow around it. Refraction occurs when waves diverge once they hit a headland, losing their energy as they make landfall around it. Diffraction occurs when waves collide and leave a hatching pattern on the surface of the water. This represents their convergence, and we can see that in the photograph in the bottom right. There's other types of waves that are generated in the ocean, and these are not caused by the wind. We have tides, and then we also have tsunami. Tides are the daily rise and fall of the ocean due to the moon's gravitational force, alternating in strength with the different phases of the lunar cycle. This illustration shows tidal range, the difference between the height of high tide and the height of low tide. The tides are generated by the interacting gravitational forces between the Earth, Moon, and Sun. Gravity is a force of attraction that all objects in space and time experience, affecting objects with different masses and distances from one another. It was discovered and described as a scientific law by Isaac Newton in 1867. Tides tend to have a very long period, usually 12 to 24 hours, depending on the types of tides that are experienced in a given area. The Earth orbits the Sun, and the Moon orbits the Earth in an elliptical path. This is due to Kepler's laws of motion and Newton's laws of gravity, which we previously touched on very briefly in our solar system lecture at the start of the semester. These paths have an attractional effect on one another, which can cause changes to the shape of the Earth, Moon, and Sun over time. The gravitational attraction of the Moon on the Earth's surface is greater than that of the Sun, and that's due to the proximity of the Moon and the Earth to each other. So the Moon is much closer to the Earth's surface than the Sun. Therefore, it's going to have a greater effect on the position and strength of the tides overall than the Moon or than the Sun will. So that's what's really going to generate the tides, is the Moon's gravitational influence on the Earth's surface rather than the Sun. So even though the Sun has a greater gravitational hold on the Earth and the Moon, because of that distance, that's what causes that difference in tidal fluctuation. As the Moon orbits the Earth, its surface changes appearance, and this is due to the Earth's shadow and the Sun's light reflecting off of Earth and Moon's surface. Only one half of the Moon is illuminated by the Sun at all times, and this is the side of the Moon that we can see. This diagram of the lunar phases shows the major phases. These are as follows. The new moon, which we cannot see in the night sky. We have first quarter, where half of the moon is blocked out by the Earth. We have full moon, where the moon surface is completely illuminated. And then we have third quarter, again, a halfway point, and finally, new moon once more. Those are our four major phases of the lunar cycle. And at each of these phases, you get differences in tide. So you're going to get points of high tide and low tide at these alternating points of phase. Those are the only phases I'd like you to know for this class. You do not have to worry about crescent or gibbous phases for the purposes of this class. Overall, the lunar cycle takes about 29 days on average to complete. So the two sets of lunar phases that generate the tides are the new and full moon, and also the quarter phases, so the first and third quarter phase. During new and full moon phase, there's a higher tide than during the quarter phases, and we can see that on this illustration. So what's happening is the gravitational hold of the moon is just slightly greater because of that alignment of the orbit between the moon and the Earth. And so because of that alignment, there's a slight bulge to the tide. And so high tide will be a little bit greater than low tide. This slide shows a GIF with spring and neap tides. Spring tides are incredibly high tides. They've got a lot more variability in their height than what we have at neap tide. And this is due to the combined influence of the Sun and the Moon and their orbital paths on the Earth's surface. So you'll note that at spring tide, the Sun, Moon, and Earth are all aligned with each other in their paths of orbit. But at neap tide, it's the opposite scenario. So the Moon is perpendicular to the Earth's position and also to that of the Sun. So because of that difference, the influence is not going to be as great at neap tide as it is at spring tide. So this does not necessarily correspond to seasonality, all right? So in this image also, the yellow portion is the solar tide, the solar tidal bulge. The gray is the lunar tidal bulge, which again is greater only because the moon is closer to the Earth's surface, and then the total is going to be the combined illustration in white. Ideally, most places on Earth will experience 2 points of high tide and 2 points of low tide in a 24-hour period in a single day. Variations in the shape of coastlines and oceanic currents can cause deviations from this ideal state. This diagram shows the periodicity of the tides. Note that there's 2 crests, or 2 points of high tide, and 2 troughs, or 2 points of low tide, in this 24-hour period. There's 3 categories of tidal patterns in the ocean. These are diurnal, semidiurnal, and mixed semidiurnal tide. Diurnal tides occur when there's just 1 point of high tide and 1 point of low tide in a day. Semidiurnal tides occur when there's 2 points of high tide and 2 points of low tide, and they're at distinct intervals. And this tends to match with semidiurnal tide pattern. It tends to match the ideal pattern fairly well, where we've got consistency in the timing of the high tide and low tide. So for example, if you're going out to the beach at like 6 in the morning, let's say you're at a time when there's high tide, right, at that point, but then 6 hours later, getting closer to about 12 o'clock, then we start hitting low tide. So there's differences there in the high and low tide, but it's consistent on a daily basis. The difference between semidiurnal and semidiurnal mixed tide is the fact that in mixed tide, the timing of those tides is different, in addition to the heights as well. So mixed semidiurnal tide is the type of tide pattern that we have here in Southern California. Again, we also have 2 points of high and low tide, but there's variability in terms of timing and height of those tides, of the tidal range. This slide shows the tidal patterns of coastlines globally. Diurnal tide patterns are in yellow, semidiurnal tide patterns are in red, and mixed semidiurnal tide patterns are in blue. Note that on this diagram, there's about a 50-50 chance of getting either semidiurnal or mixed semidiurnal tides. Very few places on Earth actually have a diurnal tide pattern. In Southern California, again, we have a mixed semidiurnal tide. So we have 2 points of high tide and 2 points of low tide with variability in tidal range and timing. Tsunami is a totally different type of waveform altogether. So tides, again, are generated due to gravity. Surface waves are generated due to the wind, but tsunami are generated due to an offshore earthquake, volcanic activity, submarine landslides, and or meteoric impact. So in other words, it's a much greater source of disturbance in that water, and that's what's going to cause the more extreme waveform to happen. The word tsunami is Japanese, and it translates to harbor wave. Tsunami events are incredibly common off the coast of Japan, Indonesia, Polynesia, Papua New Guinea, the western boundary of the Pacific Rim essentially, because the Pacific plate is subducting beneath the surrounding tectonic plates. This process of subduction will generate an offshore movement. In the case of most instances with that, you're going to get an earthquake that can trigger a tsunami event. Sometimes you'll get underwater volcanic activity or landslide events because of this tectonic force, and that in turn can also cause a tsunami. The larger the disruptive force, the larger the energy displacement, and the greater the height of the wave that's formed due to this event. Tsunami waves propagate continuously and move incredibly fast in comparison to most waves. They can travel at speeds of hundreds of miles an hour as they surge, and they can form walls of water up to 20 feet high or more. So on this illustration of how a tsunami works from the NOAA, we have an earthquake that happens, and that seismic wave will combine with the water wave, and it will create this huge continuously propagating wave that will hit the land surface. So recognize that we have breakers that naturally form with the water as the water approaches shore, and this pattern occurs because of energy displacement from frictional force. Now multiply that by hundreds of times because of the energy displacement from a tsunami, and that's why the water pulls back so far prior to a tsunami event. So it's kind of like waves that naturally crest on shore. It's just, again, magnified based on the energy displacement. One of the worst tsunami events on record, and the more recent ones, was the 2011 Fukushima tsunami. The 8.9 magnitude earthquake that was offshore of Japan created a tsunami that flooded the mainland for miles. It also led to a nuclear reactor's destruction, and damage is still being repaired today from this event. The diagram on this slide shows the time the tsunami wave from the 2011 event was felt from the epicenter of the earthquake. By the time it had reached Southern California, the tsunami event was no more than a storm surge, but the damage done to the Japanese coastline was absolutely devastating. Here are some images of the destruction the 2011 tsunami left behind as it moved on shore. It moved inland about 6 or 7 miles from the coast before receding and losing its energy. Here's the before and after of the Fukushima province in an aerial view. Before is on the left and after is on the right. Scientists monitor and warn of impending tsunami events in addition to storm surges using surface buoys and seismic stations. This combination of features and objects that we use to measure this is known as the Pacific Tsunami Warning System. Keep in mind that tsunami are often confused for another term, tidal waves. So again, tsunami, tidal waves, two different phenomena. And so with the tides, again, that's what's going on. So you've got tides, tidal fluctuation, and gravity. Tsunami, again, due to offshore earthquake, this huge displacement of energy leads to these massive waves that move inland fairly quickly. And again, our tsunami warning system that's in place, most coastal areas that are low-lying regions, they have about 30 seconds of a warning before people are asked to leave the area prior to tsunami hitting. So we are getting better with timing. There are some new tweaks to the tsunami warning system where there may be more time for people to escape. But essentially, just realize that that's one of the hazards that you have living in a coastal area with tsunami events that are frequent. So next time, we're going to continue studying oceanography. We're going to learn more about oceanic circulation. We'll also learn about ocean pollution and a little bit about oceanic ecosystems. I hope that you enjoyed this lecture, and thank you for watching.